Question? No. Then you come and ask questions right after the lecture. Yes? Well, we are talking about the speed of light all the time. Well, I will also say that, what do you mean? I will say that speed of light is not the speed of light, but there are a couple of days for that. So what would you like to hear? It's not measured. You see, how do you measure something? How do you measure length? How do you measure the speed of light? Well, okay, not that book, but let me pick up this book. They should have the exact value. No, yes. The speed of light. And no error bars. This is defined to be like this. You see, the problem is actually this one. How do you measure the speed of anything?
You provide its displacement over any time.
Okay, displacement over time. How do you measure the displacement? Which means, what do you mean by a ruler?
A predefined distance.
How do you define that distance? Okay, convenience is nice. I mean, we would like to define things based on our conveniences, but we have to somehow make a definition. So what is 1 meter? Well, the convenient length was the length of an arm. So that is how we call the 1 meter. But well, that's not precise enough for a physicist. So how do you define 1 meter as a physicist? Okay, so could you follow? So how do we now, okay, so 1 meter was this length. At some point, we also defined the circumference of Earth to be such many thousand meters. So that was another definition. The current definition is the distance that light travels in 1.1 over 2.9979245 times 10 to the power 8 seconds. This is how we define the meter. The meter is defined to be the distance light covers in this much seconds. Well, you see, we had some circular argument though. Because we started by, okay, how do we define the speed of light? How do we measure the speed of light? And then we define the quantities that we need to measure the speed of light in terms of the speed of light. So in that sense, we cannot really, well, we have to give up something. What we give up meaning that we cannot measure something. We have to define it. 1 meter, why is it this much? We defined it that way. We didn't really measure it that way. But now we are defining the speed of light to be that much. Of course, there's an uncertainty there, but the uncertainty is in the definition of the meter. What do we mean by meter? The uncertainty is not in the speed of light itself, but in the definition of our meter. The second is now defined as the, I don't know how many oscillations of a specific transition of the cesium atom. Now, these definitions are nice because cesium atom behaves the same no matter where it is. So you can call your friend in the Andromeda galaxy and talk with him, and you can write down a dictionary. You can tell him what 1 second is, and he will understand. You can tell him what 1 meter is, and he will understand. You don't need to go there and show him the meter with these current definitions. But we have a problem with the kilogram, though.
It changed recently, actually.
Yeah.
With the time constant.
Well, I think there is still some gravitational acceleration entering into that, no?
When we measure the, we have a time and the light seconds, and my friend is sitting over here, and how do we know each other's clocks are equally synchronized? How do we know this clock when the light is over here in my reference frame?
Okay. First of all, light second is not a measure of time.
It's meters?
It's a length. Okay, you will probably get your answer in a moment, but let me, at least from some of your questions, there are one point of confusion. Let me clarify one point of confusion. Let's look at the position, the x-axis. So what is the difference between the x coordinates of your friend over here and your friend over there? What will you tell me? No, my question is this one. Your friend is over there. Other friend, what's your name? Emre is sitting over there. Alper is sitting over there. I'm asking you, what is the difference in their x coordinates? It changes, right? So I can choose my x-axis to be in that direction. In that case, their x coordinates are identical. I can choose my x-axis to be in that direction. In that case, along the x-axis, Emre comes before Alper. Or I can choose my x-axis in that direction. In that case, Alper comes before Emre. So it doesn't really this question doesn't really make any sense. I have to first specify which axis I use, and then I can ask this question. Now, what special theory of relativity tells us is that the same is also true for time. So which happens before? Relative to whom? So what is the time difference between two events? Relative to whom? We don't know. You have to first specify your time axis. Specifying time axis means choosing your reference frame. And then you can ask these questions. And if you change your reference frames, just like their order along the x-axis changes if I choose different x-axis, if I choose different reference frames, the order and the separation of events might change. And there's nothing wrong with that. Everything is correct, as long as you are consistent. Now, what we are doing over here is, for example, I can come and say that, no, the separation, Emre comes first, then Alper comes along the x-axis, and they are separated by 1 meter. And then you come and tell me that, no, they are not separated at all. They are at the same x-coordinate. We will be both correct. But if we want to compare our results, we have to somehow find that translation table. How do I translate his measurements to my measurements so that we will be able to compare the two? That's actually what we are trying to do here. How do we compare the time measurements between two different reference frames, two different observables? Right? Yes?
Can't we solve this problem by or creating a causal event and asking our other friend to measure the time difference, and let us measure the time difference.
Okay.
Then ask him to then share our data and get a transforming factor.
Okay, that's what we will do, essentially. We will just figure out how we can translate the measurements from one coordinate axis to measurements in the other coordinate axis. But before continuing, let's also go back to, okay, I have been talking about the x coordinate. Okay, and we said that, okay, the x coordinate changes depending on which coordinate axis I choose. But that doesn't mean that your friends have some position. They have a position, they have their existence independent of which coordinate axis I have. So we talk about the points. And the set of points creates our what we call the space. So we have the points. They basically exist without coordinate axis. Well, it will be difficult to do computations with points without choosing a coordinate axis. For convenience, we choose a coordinate axis, then we choose the x and the y and the z coordinates of the position of that point. And similarly, in special relativity, before continuing, the collection of points makes our space. Now, in special relativity, what we have is points and time. This is what we call event. An event is a position and a time. Something happens at a point at a given time. And of course, if you want to, just like if you want to talk about the coordinates of the x, y, z coordinates of a point P, we have to choose some coordinate axis. If I want to talk about the position and time of an event, first I have to choose a reference frame. A reference frame, in a sense, is a combination of these two. But these events exist whether I choose a reference frame or not. They exist independent of me choosing my reference frames. So in a sense, you can say that the events happen, the physical reality exists, whether I choose a reference frame or not. If I want to talk about the time, which is just one of the components of this event, then I have to pick up a reference frame. And the collection of these events makes what we call the space-time. The four-dimensional space-time. 3 dimensions for the position and 1 dimension for the time. So to answer your questions, which happens first? Or what is the separation between these two events? We first have to choose a reference frame. Once we choose a reference frame, we can talk about the time of events and the position of events separately relative to that reference frame. And once we can talk about the position of events, then we can talk about their separation. But without choosing a reference frame, we cannot actually talk about the time. Now, any questions? You see, if you want to talk about the time of a given event, you have to first choose a reference frame. So whenever you are asking about the time of events, you have to specify your reference frame. Otherwise, it will not make any sense. Now, most of your confusion will arise when you are trying to compare the measurements done in two different reference frames. Depends. Now, we will see. Now, for example, different than the x-axis example that I gave, your friends, no matter where they are, depending on the choice of my x-axis, one of your friends can come before the other friend. You can just change their ordering. Now, in terms of the events, we will see that there are certain events whose order you cannot change. As your friend has pointed out, certain events are always in our past. My entrance through the door of this classroom is always in my past. For every observer, I will first enter through the door, and then I will stand here. For every observer. But your friend is scratching his face. For some observers, he probably, I mean, unless he started scratching because he was bored, he would, for some observers, he will be scratching first, then I will be speaking. For other observers, I will be speaking and he will be scratching. Now, of course, I mean, my talks about his scratching, I cannot change the order because I will not start talking about him before he did the action. Yes?
Is the T in event is essentially a function of P?
Why should it be?
Let's
You say, is your x coordinate a function of your y coordinate?
I mean, let's suppose I am in origin.
Okay.
X equals to 0, T equals to 0. My friend here is 1 light year away from me. I saw him explode.
Okay.
Then, according to my coordinate system, that event happened at T equals -1.
Okay.
Here.
Okay.
Doesn't it become a function of P?
No. Why should it be? You see, your observation is something else. What you observe, you actually see with your eyes. Basically, since light takes a finite amount of time, when you are looking at me, you are not actually seeing me at the moment that you see me. Yeah, that kind of got confusing. Okay, so let's look at the stars. That's a better example. When we see the stars, what we are actually seeing is not the current state of that star, but the state of the star at least 4 years ago. That's a different issue. But I can talk about the position of the star now. I can talk about your position now. So these two things have the same T, but different P's.
Can we compare the time between the total force? Because
Time and total force?
Net force, I'm sorry. Like when we imagine some car is accelerating direction of the x plus direction.
Okay.
Then I film that. And when I turn it backwards,
Okay.
the velocity changes and the position changes, but the second derivative of position doesn't change by time if I plot negative t to 1 second.
Doesn't it change with time? So you are exerting a constant force, right?
Yeah, acceleration, I think will point the same direction if I move it backwards again.
Well, let's come to that question when we discuss the Newton's second law. How does the force and acceleration are related? How will we describe the force and acceleration in special theory of relativity? Okay. Now let's go back to the question of simultaneity and the change of the order of events. Now, we will be basically making it more concrete, our discussions now. Yes. No, he's not bored. I mean, sorry.
Biri onun burasını taşırken gördüğü zaman sizin konuşmuş olmanız gerekmiyor mu? Onu anlamadım. Yani onun orasını
Well,
taşıması
you see, if you see, his scratching caused me to talk about his scratching, right? So the event caused the other event. We cannot change the order of these two events. But if, for example, now let's look at this example now. So basically something happens here, another thing happens here, and we have this observer over here, which sees that those two things happen at the same time. So let me be a bit more concrete. I have a light source, a light bulb. It's positioned right at the center. So when you turn on the light, there will be a light beam moving here, another light beam moving here. And, well, the speed of light is the same for both of these light beams. And then they will be covering the same distance at the same time. So what this observer will see is that the light reaches this point and this point simultaneously. In fact, that is one way that he can synchronize his clocks. So these two events, so here I have two events. Event 1 is that light beam reaches the surface on the left. Event 2 is the light beam reaches, another light beam reaches the surface on the right. So I have these two events. And according to this observer, both of these events happened at the same time. Now, of course, if you position the observer over here, he will see this event he will actually see this event to happen before this event because this distance is larger than this distance. But we are assuming that he already knows that. He knows this distance. So when he sees this light bulb to the light beam reach here, he will subtract this distance and he will be able to identify at what time the light reached over here. And he's clever enough to measure this distance also. And when he sees that the light beam reaches here, he will know how much light has taken to reach him. So he will subtract this distance, and he will also measure when this ray reaches this surface. And what he will discover is that although what he sees with his eyes will be this beam reaches here before, when he takes into account that what he sees is in fact in the past, when he subtracts those factors, these delays, he will realize that the light beam has reached this surface and that surface right at the same time. It reached these two surfaces simultaneously. You agree? Well, you see, if you are talking about such an event in between two stars, the difference can be huge.
Isn't it how exactly GPS works?
This one, well, I don't really know how GPS works, but basically, as far as I know, the GPS sends a time signal, and depending on when that signal reaches you, and so you will be able to measure how long it took to reach you, so you can measure the distance. If you know the distance of a point from 4 or 5 different points, you can pinpoint its position. So that should be more or less how GPS works, as far as I know. But I mean, in a sense, you are right. The differences are very small, so that's why in real life, in ordinary daily life, we don't observe it. But we have equipment accurate enough, precise enough to measure those things.
How do you specify cause and effect? How do you specify cause and effect?
Cause and effect?
Yeah.
Well, let me finish this one and then you ask your question. You see, for example, if I throw a chalk to you, so you will see the cause of the chalk to fly. What causes the chalk to fly will be my hand. So my hand, the motion of my hand is the cause of the motion of the chalk. That is the effect.
But you can specify for a very long time, a very long continuous chain of events, that one thing causes this, the other thing causes that. That would also be possible.
Sure, sure. So you have all these chain of events. Sure. That chain, the order of that chain is always fixed for every observer. Okay, back to this one. So this is one observer. There are these two events. The events are the beam reaches this surface, the left surface, and the beam reaches the right surface. They are simultaneous. Now let's go to another observer. The same setup. But this time, this is in a, let's say, a spaceship moving with a velocity v. And we have the observer outside. Well, when I'm saying that it's moving with a speed v, it is relative to this observer, or relative to the reference frame which is fixed at this observer. So you see, in his reference frame, what he will see. Okay, the light turns on. So the light, when they start out, they are equidistant from both surfaces. Well, we will be discussing length contraction, but this length will be contracted the same amount by this length. So still, the light bulb will be at the middle. But for this beam to reach the left surface, it will take a finite amount of time. But during that time, the left surface will move a bit towards the lamp, towards the light. So this light beam will have to travel a shorter distance than this one, because this one, once the beam leaves the lamp, until it reaches this surface, again it will take a finite amount of time. So during that time, this surface will move. So for this light beam to reach the right surface, it has to travel a longer distance. So this light beam should travel a shorter distance. This light beam should travel a longer distance to reach the respective surfaces. And keep in mind that for this observer also measures the speed of light to be exactly c, just like this observer measures. So according to this observer, the outside observer, the beam reaches the left surface before the right surface. So now we are looking at exactly the same events. The events, remember, they exist independent of the observer. There are these two events. If you look at it from one reference frame, those two events are simultaneous. They have the same time coordinate. If you look at from another reference frame, that is a different space and time axis, for a different observer, this event happens before the other event. For even a third observer, let's call this event 1. This is event 2. Let me pick up a third observer. For the third observer, the whole thing is moving in the opposite direction. For this observer, well, basically what you have is relative to the first observer, this observer is moving in that direction, this observer is moving in that direction. They're just moving in opposite directions relative to that observer. Now, in this observer, what this observer will see is that event 2, that the event that this beam reaches the right surface will happen before event 1. You see, for that observer, event 1 happened before event 2. For this observer, event 2 happened before event 1. So the order will depend relative to the observer. But if I would define a 0th event, let's see, this is observer 1, this is observer 2, this is observer 3. So event 0, light bulb is turned on. Event 1, light reaches the left surface. Event 2, light reaches the right surface. Now, for all observers, event 0 happens first. First, the light bulb is turned on. So let's see, let's order the events. for order observer 1. Well, we said that it's first event 0. Event 1 and event 2 are simultaneous. First event 0, which causes the event 1, which happens simultaneously with event 2. For observer 2, for the second observer, again, first the light bulb turns on. That is the first event. It is first E0, and then does the light reach the left surface or the right surface first or simultaneously? It reaches the left first. So E1 happens before E2. And for observer 3, again, event 0 is the cause of event 1 and event 2. But then event 2 happens before event 1. So now, even simultaneity doesn't make any sense, because it will depend on the observer.
If it's depend on the observer, can we say if observer 2 and 3 observe the events simultaneously, but they differ in the position? Can we say?
Can you repeat?
Observer 2 and 3, we assume they see the simultaneous event 1 and 2 is happening. But can we say they are different from the observer's position, because O2 is seeing the rocket goes through the right hand side, but the other one sees it goes to the left. Can we differ them from their positions?
Well, the difference is the speed, their relative speed. That is what differentiates these reference frames.
Can we specify if there is another simultaneity?
A different kind of simultaneity, you mean?
From like they have the same time, they see the events are happening at the same time, but in different positions. Like the positions are different. Like a delta x is bigger than maybe delta x prime.
Now, what we will be studying is we will be asking these questions. Does there exist a reference frame where two given events are simultaneous? So then we can define a kind of two events that are such that there is a reference frame in which they are simultaneous. For certain kinds of events, this will exist. Not for all of them. And we can also ask a different question. Does there exist two reference frames in which two events happen at the same position? You see, for example, I can take this chalk. The first event is me throwing it up. The second event is it's me picking it up. In reference frames fixed and U, these two events happen at different positions. Right? So one happened here, the other happened here. But in my reference frame, they happen always here. They happen at the same time. So for example, here we have two events which in one reference frame, at least they happened at the same time. But there doesn't exist any reference frame in which these two events happen at the same position. But in this chalk example, there exists a reference frame in which two events happen at the same position, but there doesn't exist any reference frame where those two events happen at the same time. So in a sense, we can distinguish, let's say, the events, the groups of events, let's say, whose time ordering can be changed and those whose time orderings cannot be changed. If the time ordering can be changed, then there exists a reference frame in which they happen simultaneously.
Can you please repeat the part where you said position can be same but time cannot be?
Now, this was the example.
Okay.
So I just throw it up and then pick it up. Okay. I'm not a good thrower. So listen, I'm just moving. I just throw it up and pick it up. Okay, these two events, where did they happen?
At your hand.
In my hand. In my reference frame, they happened at the same point. But in your reference frame, they were separated by, let's say, about 1 meter. Right? Sure. So what's wrong?
Evet, ben de orada takıldım. Ben mesela sizle yan yana yürürsem sizinle benim için time aynı oldu.
Okay, so we are then in that case we are both in the same reference frame. You see, for example, again, if we go back to our x coordinates, if I choose the x-axis to be in that direction, their separation will be just 1 meter. If you choose the x-axis to be in that direction, you will also say, okay, they're separated by 1 meter. So?
Me being even 1 meter apart breaks the time şey. Ya ben sizin yanınızda yürüsem de 1 metre uzakta olsam zaman farklı oluyor. Onu karıştırdım ben.
No, you see, if we are moving at the same speed, even if we are separated, our time is the same. Because my speed relative to you is 0. Nothing changes. There is no time dilation. You see, when we were discussing the time dilation, the factor that determines the time dilation is our relative speed. Your speed relative to me. But your speed relative to me is the same. Is 0, so there is no time dilation. Again, there is no time dilation in my reference frame. In your reference frame, you will see a time dilation in both of us. Your friend has a question. Well, I would rather choose, you see, what is the definition of a reference frame? The coordinate axis, origin, and, well, basically that's it. Well, if he chooses his coordinate axis to be centered, his origin centered at his position, if I choose it to be at my position, I would rather say that we are two different reference frames. But we are two different reference frames moving at the same speed. So which means that his time measurements and my time measurements will be exactly the same. His distance measurements and my distance measurements will also be exactly the same. It will not be the same because the origins are shifted. But there's a simple translation. We can make a dictionary to translate his measurements to my measurements. Okay, let's discuss. Okay, yes.
Eğer bir reference frame rotate ediyorsa aynı şey geçerli mi?
Is it an inertial reference frame? Let me ask this question first.
Sabit hızla rotate ediyor diyelim.
Okay, is it an inertial reference frame? You see, let's see. Let's assume that I'm rotating. There is a fixed reference frame I have. Okay, so what was the definition of an inertial reference frame? The first law should hold. So there's no horizontal force acting on you, right? So your horizontal speed should be the same. Okay, so let's see if it's constant in this reference frame, your horizontal speed. So let's say you are here. Now your position is changing constantly. Your horizontal speed is changing, which means that I'm not an inertial reference frame. So our arguments here need not hold because we are already restricting ourselves to inertial reference frames. You can still do the treatment for non-inertial frames, but you need the general relativity.
Is it because of centripetal acceleration?
Well, there is acceleration. Well, I'm not in. Well, what do you mean by centripetal acceleration?
When you're rotating.
Acceleration of whom? You see, in my reference frame, he will have an acceleration. He will have an acceleration in my reference frame. But there's no force acting on it. So he will have an acceleration without a force. So that means that I'm not in inertial reference frame. Okay, so let's look at length contraction. Now, there are these parts. The length contraction was kind of, I think it was the Lorentz. Let's look at the muons. There are these particles. They are called the cousins of the electron, meaning that they have exactly the same properties of the electron except than their masses. They are just 200 times heavier than the electrons. They have the negative electric charge. And hopefully we will be also discussing the spin. They have the same spin. They have exactly the same properties except than the mass. And they also have a finite lifetime. So if you have a muon, it decays into an electron and two other particles that we call the neutrinos. Now, for our discussion, it's not really important what these neutrinos are. Now, the first time we observed the muons was in so-called the cosmic rays. So what happens is we have the Earth. There are all kinds of particles coming from the cosmos. And when they hit the atmosphere, they create the particles called the pions. Now, they're also the pions should be, let's see, somewhat have the same mass as the muons, more or less. And they're also not stable. The pions decay into muons. And plus other particles. So this is where they are created. So when there's a cosmic ray, it creates the pions. The pions, they decay, and they decay into muons. And muons, they also have a finite lifetime. So at least in the rest frame, if you would have a muon at rest, it will stay as a muon for some time. Let's say for a time tau 0. So in the rest frame, it has a lifetime tau 0. And they are moving close to the speed of light. If you say that D is the thickness of the atmosphere, now tau 0 times C turns out to be much less than the thickness of the atmosphere. But still we observe muons we see many muons on the surface of the Earth. They are created on the upper regions of the atmosphere. They travel very close to the speed of light. Okay, this is less than C times D. And even if you would apply Newton's dynamics, even if they move with the speed of light during their lifetime, they shouldn't be able to reach the surface of the Earth. But they do. Now we already know why they do, how they do. And the answer is? I'm not moving, I'm the observer on Earth. There is no length contraction here. It's the time dilation. You see, muon lives, let's say, 10 to the power minus 10 seconds. During that time, it should be able to cover only 1 kilometer. But since it is moving very close to the speed of light, its clock is ticking very slowly. Its clock shows 10 to the power minus 10 seconds, but my clock shows, I don't know, 10 to the power minus 9 seconds. So if its speed is very close to the speed of light, its self-clock will tick very, very slowly. So the actual distance it will be able to cover will be this much. This is the dilated time times c. So it's not just tau c, it's tau divided by this factor multiplied by c. So this is from the perspective of an observer on Earth. Now let's imagine what does the observer, if there was an observer moving with the muon, we'll see. There won't be any time dilation. So the muon will die in 10 to the power minus 10 seconds. And that time, but at the same time, the atmosphere is moving past the observer. You see, in here, in this reference frame, there is the muon. Let's say the muon is created over here and is moving towards the Earth. So we are the observer on Earth following the muon. So the muon will live much longer than tau 0 because of time dilation. It is moving very close to the speed of light. So its own clock will tick slower in my reference frame. So it will live much longer. Now we go back to the other observer, moving with the muon. Since he is moving with the muon, the clock of the muon will be just flowing at its ordinary speed. So it will just live 10 to the power minus 10 seconds, let's say. At the same time, the atmosphere is moving in that direction now, in this new reference frame. Do you agree? The others? You see, if the observer is moving in this direction, in the Earth's reference frame, in the reference frame of the observer, the Earth is moving in the opposite direction. So if I'm moving in this direction, you are all moving in that direction, actually, in my reference frame. So there's no time dilation effect here, but the muon still reaches the surface of the Earth. And the atmosphere is now moving with the speed v. So how come the muon reached the surface of the Earth now? You see, I'm here. Let's imagine I am the muon. This is the top of the atmosphere, and that point is the surface of the Earth. My clock is ticking. You see my clock. As I'm moving, you say that, my clock is slowing down. So I will live much longer than my lifetime. So I will be able to reach the surface of the Earth. Now I am the observer. The muon is just moving with me. So here's the muon. So we are just moving. I look at his watch. His watch is moving just at the ordinary speed. It's just flowing ordinarily. So he will only live 10 to the power minus 10 seconds. And in 10 to the power minus 10 seconds, let's say he will be able to travel a distance which is half the thickness of the atmosphere. But still, it should reach the surface of the Earth. Now, in this reference frame, the muon is at rest. It's just over here all the time. Just put yourself on my shoes. It's always over here, but you are moving in that direction. You're all moving in that direction. But still, the muon lives until all the atmosphere passes by and then dies. But it shouldn't be able to live that long. It cannot stay alive for such a distance to pass by. So how come? One of you had already given the answer.
In one perspective, there is a time dilation, and from the other perspective, there is a length construction. That's why we don't see the length shorter than we see.
Yes, exactly. The idea is, let's say, let me put in some numbers. Assume tau 0 is such that tau 0 times c is equal to d over 2. So if nothing happens, if Newton's dynamics were correct, the muon, once it is created, it should decay midway. But then we say, no, there's time dilation. The spatial relativity tells us that there will be time dilation. And it tells me that, let's say, 1 over square root of 1 minus v squared over c squared is 2. The v is such that this factor is 2. And then the tau, the total lifetime in this reference frame is this much. This is twice tau 0. And the distance it covers it will live a lifetime tau 0 with a speed v, and tau 0 and v such that let's just assume it's d over 2. Now it will cover the distance tau times v before it decays. Once it's created, it will live this long. And it's moving at this speed, tau times v, so it will be just d. It is twice tau 0 times v, twice d over 2 is d. So from the point that it is created, it just covers all the atmosphere, and when it reaches Earth, it decays, and we see it in our detectors. Let's just assume that the numbers are such that these are satisfied. This is from the reference frame of Earth. Fixed on Earth. Now let's look at the reference frame fixed on the muon. So in this reference frame, muon is fixed over there. There is the Earth with its atmosphere. They are all moving with a speed v in this direction, in this new reference frame. Well, the muon will live a total time tau 0. There's no time dilation. So all this atmosphere, etc., can only move by a distance tau 0 times v, which is d over 2. So all this atmosphere and Earth could only move by d over 2. And what we said is muon is created at a point, and the distance to the surface, if it is created over here, when it decays, it is on the surface of the Earth. So here in the above reference frame, the muon is created over here. It travels a distance d, and when it reaches the surface of the Earth, it decays. So this distance was d. But if the muon decays on the surface of the Earth, for every observer, it will decay on the surface of the Earth. But until the surface of the Earth, the muon can only travel a distance d over 2. So in this new reference frame, this distance should be d over 2. So the length should be different for different observers. Well, by the way, that factor 2, remember, is this one. if instead of this factor you had put 3 or 5 or whatever you like, instead of that 2 over there, you will get exactly the same thing. So that length, let's say L0 is the length of something measured in its own reference frame, in the reference frame in which it is at rest. And L is the length measured in a different reference frame. Then L is just L0 times, or L0 over 1 over square root of 1 minus v squared over c squared, or this is L0 times square root of 1 minus v squared over c squared. This is called length contraction. L and L0 are measured in the direction of the speed. In the direction of velocity, not in the perpendicular direction. Length in the vertical direction are not contracted. And in the next hour, we will discuss why they are not contracted.
Are those aforementioned particles point-like as they have size?
Which ones? Muon, as far as we know, is point-like.
I was wondering if this...
Anyway, let's go for a break, and then we can discuss your questions during the break. Okay, see you in 10 minutes. Yakınsa. İlla olması gerekmiyor. Gidiyor zaten.
Gidince o zaman time distance travel sonsuza gidiyor.
Neyi?
Distance travel'sı sonsuza gidiyor.
Evet. Yani ölene kadar, sonsuza kadar yaşar. Çünkü hiçbir zaman ölmeyecek.
O zaman D bölü 2 diye hani bir şeyimiz kalmıyor ki. Alması gereken bir distance.
Yok şimdi sorunun tanımı şu. Diyorum ki müyon burada yaratıldı, oluştu. Şurada yok oldu. Aradaki mesafe D dedim. Eğer şey olsa, ışık hızına yakın, çok yakın hızda giderse o zaman daha da uzun mesafeyi cover edebilecek. Tam ışık hızında gidebilse sonsuza kadar yaşayacak zaten, hiç yaşlanmayacak.
Bir de şey demiştik ya biz, eşittir 2'ye, D bölü 2'den eşittir 2'ye çekmiştik ya. Şuradan o zaman direkt onun hızını bulamıyor muyuz hocam?
Bulurum. Yani burada sayıları attım. Ama 2 değil de yani bulurum hızını. Ama yani 2 olması gerekmiyor. Bu faktör 5 de olabilir, 20 de olabilir senin problemine göre. Yani somut bir örnek olsun diye oraya 2 olsun dedim.
Aklıma kuracaktı da orası 2 olunca mesela hani D'ye bayağı bir yakın olmuyor. Sadece yakın.
D'ye çok yakın değil.
Aynen. Biz yakın diye konuşmuştuk. O yüzden bir böyle bir kafa.
Şimdi yakını nasıl tanımlıyorsun? Yarısı yakın mıdır? Mesela o yarısından daha yakın sanırım.
Haklısın. Öyle düşünüyorum.
Yarısından daha yakın.
Hocam ben tamamlıyorum. Yani aslında olarak, bir ön söz olarak anladım da neden o yani particle'ın dünyaya düştüğü her gözlemci için aynı bir fenomenmiş gibi oluyor.
Yani şöyle diyelim. Geldi sana çarptı. Tamam. 2 tane olay var. Müyonun sana çarpması ve sana miyonun çarpması. Tamam. Bu iki olay aynı zamanda aynı yerde oluyor. Şimdi birazdan şeyi göreceğiz mesela. Lorentz transformasyonlarını göreceğiz. İki olay belli bir referans sisteminde aynı anda ve aynı yerde oluyorsa bütün referans sistemlerinde aynı anda aynı yerde olmak zorunda.
Peki mesela bana çarpmasaydı tam şuradan şöyle geçseydi.
Şimdi aynı anda ve aynı yerde olan olaylar her zaman için aynı anda aynı yerde olacak. Beni ilgilendiren kısmı da o. Yani dünyaya çarptı, öldü. Yani tamam sana çarpmadı ama atıyorum geldi arkadaşına çarptı. Ya da şuradaki hava molekülüne çarptı.
Hocam main textbook olarak Bayezid'i mi kullanıyorsunuz?
Bayezid'i kullanıyorum.
Tamam. Hocam ufak bir şey, böyle bir örnek vermiştiniz ya. Bu hareket ettikçe ışığın tam şeyden çıktığı, ampulden çıktığı andaki o andan sonra bu mesafenin kısalması gerekiyor. Çünkü gemi böyle gidiyor. Işık hızı sabit.
Ve sonlu.
Sonlu. Ama length'in de değişmesi gerekiyor.
Değişsin. Beni ilgilendirmiyor ki. Yani şunun değiştiği kadar bu da değişiyor. Sonuçta dışarıdaki gözlemci için o aradaki mesafeler farklı. Ama önemli olan şey ne? Lambda'nın o surface'lara olan mesafesi aynı. Beni ilgilendiren şey de o.
Hocam ben şeyi merak ediyordum. Şimdi bu adam buradan bakıyor ya. Aynı şekilde bunun mirror image'ında bir adam daha bakarsa.
Baksın şuradan baksın.
İki farklı reference frame olmuyor mu?
Olsun, birbirlerine göre sabit hızla giden iki referans sistemi var.
Ama iki referans frame'de bu zaman az önce dediğinize göre aynı position olmuyor.
Position'dan bahsetmiyorum
Position
ki.
olmuyor.
Ben position'ları farklı olacak ama o beni ilgilendirmiyor. Beni ilgilendiren zamanları. Yani şu da olabilir. Sen saatini kaydırmış olursun, farklı zamanları ölçersin. Ama iki olay arasındaki zaman farkını aynı ölçersin. Beni ilgilendiren şey de burada o. Zaman farkları.
Absolute bir şekilde yapılması gerekiyor.
Absolute time diye bir şey. Yani referans
tabii fark manasında.
Evet, farka bakıyorum. Yani fark sıfırsa aynı anda oluyor diyorum. Fark pozitifse işte hangi farka baktığıma göre biri öbüründen önce olmuş diyorum. Negatifse öbürü ondan önce olmuş diyorum.
Niye? Ya time dilation oldu ya da length contraction oldu.
Evet.
O zaman herhangi bir şekilde bir relatif bir durum varsa, relatif bir hız durumu varsa ya time dilation olmak zorunda ya da length contraction.
Niye öyle olsun ki?
Zorunda değil mi?
Hayır.
Olmadan da tutabilir yani.
Hayır,
Birbirine göre
yok. Şimdi biz burada iki tane referans sistemi aldık. Özel referans sistemleri aldık. Evet. Birisi duruyor, öbürü hareketli. Öbüründe de öbürü duruyor, diğeri hareketli. Bir üçüncüsünü düşün, ikisi de hareketli olsun.
Aynı.
Hem length contraction olacak hem time dilation olacak.
İkisi aynı anda da olabilir.
Niye olmasın?
Ama bir şekilde bir kayma olmak zorunda ya, bir ikisinden birinde. Ya da ikisinde de aynı şekilde. Dengelemek için relativite varsa kesinlikle.
Şimdi sonuçta her gözlemcinin hemfikir olması gereken şeyler ne? Müyon yaratıldı belli bir noktada. Ve müyon surface'da bozuldu. Surface'a kadar geldi, surface'da dağıldı. Bu iki olayda her gözlemci hemfikir olmak zorunda.
Evet. Bir şekilde ulaşıyor. Bunu her reference frame ile consistent yapabilmek için bir şekilde...
Yani şöyle düşün, mesela atıyorum müyon şöyle gidiyordu diyelim ki sen müyonla aynı hızla gitmiyorsun da yarı hızda gidiyorsun. Müyondan daha yavaş gidiyorsun. Ne göreceksin? Sen dünya böyle geliyor. Müyon böyle geliyor. Müyon biraz yavaşladı, çok fazla yavaşlamadı. Bu mesafe biraz küçüldü, çok fazla küçülmedi. Ama aynı zamanda ikisi zaten birbirine doğru da hareket ettiği için yine yani aradaki mesafe kadar seyahat etmiyor müyon. Evet. Ama müyon artı dünya aradaki mesafe kadar seyahat ediyor.
Peki bir şey daha soracağım. Bu dördüncü dimension dedik de sanki çok oturmuyor gibi yani. Normal bildiğimiz geometri.
Dimension dediğin şey ne diye sorayım sana?
Linear independent olması diye.
Tamam, zamanı konum cinsinden yazabiliyorsan yaz. O zaman o şey dimension değil derim de.
Tam olarak yani kafada yani şu an düşündüğüm gibi olmuyor.
Ya şöyle şimdi 3 boyutu niye 3 boyut diyoruz? Niye 3 boyuttan 3 diyoruz boyut sayısına?
Neden 3 diyoruz? Yani space'i tanımlayabildiğimiz
Nasıl tanımlarken ne tanımlıyorsun? Nasıl tanımlıyorsun?
İşte başlangıç noktası 3 tane unit vektör.
Ha, 3 tane birim vektör diyor. Şimdi birim vektöre niye ihtiyacın var? Belli bir noktayı belirlemek için 3 sayı vereceğim diyorsun.
Evet.
3 sayı verdin, tamam, o noktayı tanımladın. Ama belli bir olayı tanımlamak istiyorsan benim 4 sayıya ihtiyacım var.
Bir de zaman.
Bir de ne zaman olduğunu tanımlamaya ihtiyacım var. Ha, mesela Newton mekaniğinde kalıp bunu aynı argümanı yine yapabilirim sana. Ama şimdi birazdan göreceğiz. Newton mekaniğinde zamanla diğer koordinatlar birbirine karışmıyorlar.
Farklı.
Şimdi yani atıyorum mesela farklı koordinat eksenleri ne olacak? Mesela Newton mekaniğinde şöyle bir koordinat ekseni seçtim, böyle bir koordinat ekseni seçtim. Zamanı ikisinde de aynı olacak. Ama ne olacak? Mesela bu koordinat eksenindeki belli bir noktanın x bileşeni, konumun x bileşeni, diğer eksende ki x, y, z bileşenlerinin bir toplamı olacak. Sen eksenlerini dön derdiğin an x, y, z bileşenleri karışıverdi birbirine. Şimdi şeyi göreceğiz. Bu Lorentz dönüşümlerine bakınca bir referans sisteminden bir başka referans sistemine gittiğin zaman bu zamanla diğer koordinatlar karışıveriyor birbirine. Ayıramıyorsun. O yüzden biraz da 4. boyut diye kullanıyoruz.
Vakit var mı?
Var, bir iki dakika daha var.
Şimdi hocam ilk başta şöyle bir soruyla başlayalım. Işık hızı medium'dan medium'a değişiyor değil mi?
Değilsin.
O değişsin, tamam. Bir tane event düşünün hocam. Uzaktan da işte sesi gözlemliyor. O fakat bu eventin işte herhangi bir noktasında işte bir olay oluyor, patlama oluyor, bir şey oluyor. O sesin medium değişiyor.
Bunların hepsi boşlukta.
Hepsi boşlukta bunların hepsi. Peki benim kurduğum işte benim düşündüğüm gibi düşünürsek oradaki eventlerin çakışma olasılığı var mı? Yani üst üste görme olasılığı sadece gözlemde.
Medium'u tamamen işin dışına çıkarman lazım.
Bunların hepsini, buradaki yorumların hepsini yapabilirim.
Şimdi daha sonra diyeceğim mesela, daha sonra şöyle bir laf edeceğim. Buradaki C aslında ışık hızı değil diyeceğim. Evrensel bir sabit. O yüzden ortam olmuş, olmamış hiç fark etmez.
Astronomi sabit gibi mi hocam? Newton'un Einstein sabiti gibi mi?
Einstein sabitinden ziyade Newton sabiti gibi. Bir sabit.
Zaten sabit
Işık o hızla gidiyor. Boşlukta. Boşlukta. Yani burada ışık hızı diyoruz da ışık çok da kritik bir şey değil.
Hocam ben de zamanla ilgili bir şey sormak istiyordum da. Hani eventlerle ilgili sormak istiyordum daha doğrusu. Şimdi mesela bir yumurtayı kırdığımızda hocam ve onu filme çektiğimizde eventin E0'ı bulabiliyoruz. E0 ve E1'i görebiliyoruz. Ama onu bilardo toplarıyla yaparsak hocam, bilardo toplarının birbirine vurduğunu filme çekersek hangi eventin nerede ve ne zaman olacağını bilmiyoruz. O causality yok oluyor. Bunu nasıl yapabiliriz hocam?
Causality orada yok olmuyor. Kaotik bir sistem oluyor.
Yani ben kaotik bir sistemi çeviriyorum.
Yani sistemin kaotik. Yani ne olacağını öngöremiyorsun ama sen filme çektiğin zaman neye yol açmış, o neye yol açmış onu gayet de görebiliyorsun.
Ama zaman bu tarafa mı gidiyor, bu tarafa mı göremiyorum. O yumurta örneğin zaman ileri doğru artıyor. Bunu anlayabiliyorum.
Direction of time mı diyorsun?
Evet.
Şimdi orada şeyi karıştırma ama. Mesela bilardo topları örneği olsun. Gayet simetrik diyorsun. Ben onu seyrettiğim zaman gerçekte hangi olayın neye yol açtığını söyleyebiliyorum.
Evet, biz farklı bir referans verdik.
Tam tersi olaylar da mesela A B'ye, B C'ye yol açıyor. C'nin tersi B'ye, B'nin tersine, B'nin tersi de A'nın tersine yol açabilir. Bununla ilgili bir problem yok. Mesela aynı durum yumurtada da var aslında.
Öyle mi?
Termodinamik dışında, termodinamiği bir tarafa bırak. Yumurtanın mesela Newton denklemleri ya da kuantum mekanik denklemleri falan düşün. Yumurtanın bir araya gelip tekrar kırılmış yumurtanın bir araya gelip tek yumurtayı olmasını engelleyen hiçbir doğa yasası yok.
Yani düzensizlik dışında bir şey, entropi dışında.
Entropi dışında. Entropide ne kadar mikroskopik bir olay soru işareti.
Hocam bir de şey vardı.
Hadi derse başlayalım.
Dersten sonra.
Açılacak mı? Yani açılacak.
Açarız. Sekreterliğe bir dilekçe ver. Yani her boş bulanda kaydolayım bari neymiş diye gelmesin de.
Yok hocam.
Yani
Ya ihtiyacı olanları ekleriz. Şey değil, dert değil.
BB'den almak istiyorum.
I just want to clarify one point. Now, when we said we are always talking about c being the speed of light, c is actually a fundamental constant. Of nature, of the universe, in fact. Just like the Newton's constant, the h bar, just like they are constants, c is a constant. And it just turns out that light moves with this constant in vacuum. So one of you were asking what happens if we have a medium. Well, nothing really changes. Because whenever we are talking about the speed of light, we are not talking about the light actually. We are talking about this fundamental constant. If there is a medium, well, fine, then light is not moving with this fundamental constant, but this fundamental constant is still the same. The medium doesn't change this fundamental constant. It just changes whether light moves with a speed equal to this fundamental constant or not. So all our treatments over here still hold. Now, any questions on this length contraction?
The reason I asked the size of the particles, I was wondering if this length contraction is relevant in any scientific measures.
Sure. You see, we are colliding ions. In LHC, for example, especially we are colliding lead ions. And when they are moving very close to the speed of light. And when you are trying to make estimates about their properties, what will happen, we don't imagine spherical nuclei. The nuclei that are colliding in LHC have this shape. Because of length contraction. They are very narrow. So we should take that into account.
So actually C is the speed of light in vacuum, right?
Well, the more precise way of putting it is that the speed of light in vacuum is equal to c.
Okay. So in this case, can we say that time for a photon in vacuum is undefined and length for a photon in vacuum does not exist?
Well, let's say the universe, the three-dimensional universe, let's say, for the photon is actually two-dimensional. Because you see, if the photon is moving in that direction, it's not aging, its time has stopped. Plus, the size of the universe in that direction is 0,
Yes.
but not in the other direction.
I was talking about. So what
But
about time?
time stops.
Time stops, sorry. Okay.
But we will never be able to talk about if we move with the photon. We will never be able to.
Hocam tek konuyu fazla dağıtmak istemem ama sanki hocam ışık hızıyla evrenin genişleme hızı arasında bir sıkıntı vardı. Yani öyle şeyler hatırlıyorum bir de. Böyle sanki evrenin genişleme hızı ışık hızından daha fazlaydı. Hatta o yüzden bazı karanlık bölgeler kaplandı.
Okay, that is true, but I mean, do you mind if we continue these discussions after the lecture, I mean, there are many blackboards around. We can continue there.
Şey sormak istiyorum. Bu şeyi de bozmuyor mu? Hani fizik yasaları evrenin her yerinde geçerlidir şeyinde mi?
No. You see, okay, I'm trying to avoid general relativity, but you are trying to go into general relativity. You see, one problem your friend was mentioning is that we look at the universe. There is a microwave background radiation, which corresponds to something like 2.7 Kelvin. So when somebody tells you that the space is not at 0 Kelvin, but the temperature of space is 2.7 Kelvin, what they actually mean is that it's this microwave background radiation. And that is something we will study, by the way, when we discuss the black body radiation. How do we get this 2.7 Kelvin? But then there is a problem. If you look at the universe in that direction, and the universe in that direction, they have the same temperature, more or less. Now, the deviation is very small. But that part of the universe couldn't have yet influenced that part of the universe. So they can, if you talk about the cause and effect, I mean, these two parts are completely independent. That part is not in the past of that part, in a sense. They shouldn't be influencing each other. But if they are not influencing each other, how come they are at the same temperature? There's no need for them to be at the same temperature because they couldn't yet communicate. So it's just like you are picking up a random number at home and your other friend picks up a random number, another random number at home, at his home, and you don't communicate with each other and you just realize that you have picked up the same number. So it's just like the universe had picked the same temperature at completely unrelated regions. Now, one way to explain this is that the expansion of the universe. But of course, we have to assume that the universe should have expanded faster than the speed of light. So that these two regions were able to communicate in the past, but then they moved faster than the speed of light, and now they are unrelated. But then you will complain, how come they can move faster than the speed of light? We will say many times that nothing can move faster than the speed of light. Now, the distinction there is that what general relativity does is that it describes the universe as let's say, a large balloon. Just imagine a balloon. If we were in two-dimensional, if the space was two-dimensional, you can just model it as the surface of this balloon. And let me also imagine that we are blowing up the balloon. This is the typical. Yes. Well, there are actually two different kinds of speeds we should be paying attention to. One is my speed relative to space at my position. And the other one is how fast our separation is increasing. These two things are not necessarily the same thing. Just imagine a balloon, and you put some dots on the balloon. Those dots might be at rest on the surface of the balloon. Okay? But if you blow up the balloon, although these dots are not moving on the surface of the balloon, their separation will increase. So imagine instead of fixed dots, there are ants on the balloon. Well, the ants will be able to move, 1 kilometers per hour. That will be their maximum speed. So if there are ants, the fastest that their distance, if you have the balloon, you are not blowing up the balloon. If these are ants, their separation can at most separate by 2 kilometers per hour. But if the balloon is expanding at the same time, then their separation can be increasing much faster than these 2 kilometers per hour. So there are basically two speeds over here. Well, two different concepts. One is the speed of the ant relative to the surface of the balloon. The second one is the expansion of the surface itself. Now, when we say that in special theory of relativity that nothing can move faster than the speed of light, what we are actually saying is that in the analogy with the balloon, the ants cannot move faster than the speed of light relative to the surface of the balloon. But that doesn't mean that the distance between two objects cannot increase faster than c times time. This separation can increase faster than the speed of light. There is nothing that restricts that. But each one of them separately cannot move faster than the speed of light relative to the surface at their position. Well, I mean, we will come to that, but I mean, there are some other things we have to discuss before. If you also follow the historical development, first it was the speed of light. It was actually the speed of light. But then we realized that it's not really the speed of light itself, but rather some fundamental constant of nature. And the light turns out to be moving at that speed in vacuum. Other questions? Okay, let's go to the Lorentz transformations. Well, I'm kind of changing the order of the subjects in the book, but I would rather follow your questions than follow the book. We will just complete whatever we had skipped. Yes, I will, hopefully. So now, before going to Lorentz transformations, what we are aiming at, you see, if we stick with three-dimensional coordinates, let's say I have some axis, x and y, and then your friend chooses some other axis, x prime and y prime, and then we have a given point. There is this point. Well, your friend will say that that point P has the coordinates Px prime and Py prime. So this point P will be Px prime in the x direction plus Py prime in the y direction. But I will say that it has the same point has the coordinates Px in the x direction and Py in the y direction. Now these are x primes. Px in my x direction plus Py in the y direction. And in fact, these two expressions, although we have different components, different x and y components, they are the same thing. Now, how are they related? Well, I can say that Px prime is just r times x, a unit vector in the x prime direction. But r is also this quantity over here. So Px prime is actually Px times x dot x prime plus Py y dot y prime. And let's assume that these two coordinate axes are rotated by the angle theta. You see, x hat vector is this vector, x prime vector is this vector. The scalar product is just the product of the magnitudes, which is just 1 times the cosine of the angle between the two. So this is Px times cosine theta plus Py times no, sorry, that's not y dot y prime, that is y dot x prime. Well, these are vectors with unit norm, so the y hat times x prime is just the angle, the cosine of the angle between the two, so it's cosine pi over 2 minus theta. So Px prime is Px cosine theta plus Py sine theta. And if you like, you can also calculate py prime, which will turn out to be minus px sine theta plus py cosine theta. So this is, in a sense, is my dictionary. If I measure the coordinates, px and py, and your friend wants to compare it with his results, he just needs to put my px, py over here, obtain what he should be measuring in his own coordinate axis. And that's exactly what we will do with this in special relativity now. So we have, rather than just rotated axes, we have two different reference frames. Pi over 2 minus theta. It is just this angle over here. Pi over 2 minus theta. So what we will do is we will take an event, the same event, and we will just try to find some translation between the positions and time measured in one reference frame with the position and time measured in the other reference frame. And after that, remind me about the vertical length contraction. I forgot that. Anyway, after this. Okay, so I will assume that I don't want to deal with translations. At t is equal to 0, I have two reference frames. At t equal to 0, they overlap. Their origins overlap. X, y, x prime, y prime. Now, let's assume that the event happens over here. And the O prime observer measures that event to happen at the time t, at the time t prime, at the x coordinate x prime. For the time being, I will not be worried about the y and the z coordinates. Just the x. The O prime reference frame is moving in this direction with a speed v. Well, I can always choose the direction x-axis to be in the direction of the speed. So I can, without losing any generality, I can just assume there's no y or the z components of the speed. And the same event, the O observer will measure that it happened at the time t, at the point x, at the point with the x coordinate x. So how will we be able to translate the two? That will be our question. Now, for observer at O, well, this distance is x prime, as measured in the O prime reference frame. So the O observer, we'll see that that distance is just O prime times square root of 1 over 1 minus v. No, that distance is x prime times square root of 1 minus v squared over c squared. I'm trying to write x. Now, x should be this distance measured by this one. And he will say that it is just, it's moving with a speed v for a time t. It should be v times t plus this distance, the distance of x prime from the O prime, but he knows that the observer in O prime had measured it to be x prime. So in the O prime reference frame, that distance is x prime. But that means that in his reference frame, that length should be contracted by by this factor. So this is the distance. So x should have this form. Now let's look at the observer O prime. Well, for the observer in O prime, O is moving in the opposite direction with minus, well, let me just draw it also. This is moving with a speed minus v. He knows that, well, this point is at a distance minus vt in the opposite direction. It's minus vt. He knows that O observer had measured this distance to be x. But he will see that the distance contracted. So it will be minus vt plus x square root of 1 minus v squared over c, or 1 minus minus v squared. So the observer in O prime concludes that x prime, sorry, this is t prime. X prime, t prime, and x should be related by this relation. And observer in O concludes that xv and xt and x prime should be related by that relation over there. Well, what we are trying to do is we are trying to relate x and t with x prime and t prime. Well, these two are enough. So let's try to find x prime and t prime in terms of x and t. We have two unknowns and we have two equations. Well, the first equation, let's say this is 1, this is 2. The first equation tells me that x is equal to 1 over square root of 1 minus v squared over c squared times x prime plus vt prime. This is this equation. Let's go to the second equation. And from the second equation, I will solve t. The second equation tells me that t is equal to 1 over v x minus x prime times square root of 1 minus v squared over c squared. But I already know what x is in terms of x prime and t prime. X prime plus vt prime minus x prime square root of 1 minus v squared over c squared. Well, let me simplify it a bit. 1 over v. If I take into parentheses of x prime over 1 minus v squared over c squared, I have 1 minus v squared over c squared. Plus vt prime over square root of 1 minus v squared over c squared. Well, this minus cancels this minus. Now this 1 cancels this 1. Minus makes a plus. I have 1 over v over here. It cancels one of the v's here and also the v over here. So t is just 1 over square root of 1 minus v squared over c squared x prime, now t prime, plus v over c squared x prime. Well, this part is just the algebra. You have two equations for the two unknowns x and t. We are assuming x prime and t prime are known. We just want to translate them into x and t. You have two equations for two unknowns. If you solve for them, this is what you get. Well, most of the time you define this 1 over the square root of 1 minus v squared over c squared to be gamma. To simplify this calculation, this expression, so x is equal to gamma x prime plus v t prime, and t is equal to gamma t prime plus v over c squared times x prime. Now also keep in mind what these transformations are. I am one observer, one reference frame. There is another reference frame moving in the positive x direction with a speed v. In that reference frame, one observer at rest in that reference frame measures the time of an event to be t prime and the position of that event to be x prime. And at t equal to 0, our origins overlap. So when my watch is t equal to 0, that reference frame was right over here. And at that time, he also set his time t equal to 0. So t prime is equal to 0 and t equal to 0, they match. Then, of course, he continued. So he measured the event to be happening at the point x prime at the point t prime. If he had measured the event at the point x prime at the point t prime, then I have measured exactly the same event at the point x and at the time t. This is what these equations are telling me, how to go from one reference frame to the other one. You see, one of you were asking during the break, why do we call the time the fourth dimension? Now, if you go back to this example, this simple reminder, let's say, if you just change your axis, the x and the y components, they just get mixed up. So you cannot really say that some quantity is purely x. Okay, it might be purely x in one coordinate axis, but not purely x in the other one. Now, if you look at these Lorentz transformations, if you go from one reference frame to the other reference frame, x and t, they also get mixed up. It doesn't really make sense to talk about a pure time or pure position. According to whom? If you identify something as pure time in one reference frame, it will be a mixture in the other reference frame, and all reference frames are equal. So in that sense, it doesn't make sense to separate the position and time as two independent quantities. Any questions on these? Now, of course, I didn't write it over here. Y is equal to y prime and z is equal to z prime. Y and z are the distances in the vertical direction, in a sense. Now, why doesn't the distances in the vertical direction contract? The thought experiment to prove is this one. Let's imagine a thought experiment. There is a train. Let's say I am the train. I'm just moving in one direction. And somewhere along the line, I'm a passenger in the train. Somewhere along the line, there is something to put some marks. Now, in the reference frame of the station, this is at rest. There is this wall. I'm just moving with some speed v. And no, let's just imagine this one. Let's just imagine there is a mark at this height, right over here. And I keep there's a pen in my hand exactly at the same height. In the reference frame of the station, let's just, for the sake of argument, assume that in your reference frame, if I'm moving in that direction, the there is a length contraction in the vertical direction also. So what will happen is, if we assume that there is a length contraction in the vertical direction, as I move, you will see my vertical height to be contracted. So this height will be over here. So I should be marking below that line as I am crossing. Do you agree? But now let's look at the reference frame of the train. I am at this height. I am at rest. That is moving. The line is moving. So as it's passing me, it should go down. It becomes smaller, shorter, if there is a contraction in the vertical direction. So since it becomes smaller, when it passes me, I should mark above the original line. Then we stop the train. We go and look. Where do I mark? Do I mark below or above? There can be only one mark. And since the two observers cannot agree, no matter what they do, it cannot go below or it cannot go above. It should be exactly at the same height, which just shows that there cannot be any length contraction. You see, contrary to twin paradox, in the twin paradox we could argue which observation we will see, because one reference frame was a non-inertial reference frame. In this example, we can always cook up the system such that all the observers are always in the same inertial reference frame. Yes? Is? Well, you see, we are moving with the same speed in the sense that if I am moving with a speed v according to you, and you are moving with a speed v according to me, and just in the opposite direction. If you look at the two equations, we are over here. You see, essentially the same thing happened. These two equations are identical equations with the exchange of the coordinates and change of the sign of v. But this factor, the gamma factor, doesn't depend on the sign of v because we are taking the square. Since gamma factor is the same, the length contraction should be the same, if there is any.
If you imagine going in this direction, if length contraction and vertical direction happen, could we pass maybe speed of light even if we did bump a little bit in vertical direction, since that length is contracted now?
No.
According to an outside observer.
Now let's look at how do we add the speeds. Okay. So you are basically saying that, okay, we are moving very close to the speed of light. So if I move my hand vertically upward, will my hand be moving faster than the speed of light?
No, I'm not doing that. We are moving.
Okay.
Imagine the length contraction in vertical axis happens.
It doesn't happen.
I'm trying to say if that happened, it would change something. Yani şeyi kastediyorum hocam aslında. Biz bir yönde giderken o aslında dışarıda o yönü kısalmış olarak görüyoruz ya.
Okay.
Öbür yönde kısalıyor olsaydı çok az bir hızlanmayla o aksiste çok uzun mesafeler kat edemez miydik? Yani
But it doesn't happen.
Katmış olmuyor.
I don't think so. I mean, you might try to cook up, but I don't see why, how. It just doesn't happen. Anyway. Other questions? Let's add the speeds. Okay, and then we will end today's lecture. Well, let's see. What is the speed of an object? The x component of the speed of an object for one observer. Well, the change in x divided by the change in time t. This would be the speed, Vx. Which should be equal to, if we just look at this gamma factor, assuming that we are following an event, following an object. So we just have two events, we measure its position at one time, we measure the position of it at the successive time. So we have this delta t, we have this delta x. Well, this delta x will be related to delta x prime and delta t prime in the other reference frame by that relation over there. So delta x will be just gamma delta x prime plus v delta t prime divided by, and delta t will be gamma delta t prime plus v over c squared times delta x prime. Gamma factors, they will cancel. I can divide the numerator and denominator by 1 over delta t prime, which will just give me Vx is equal to delta x prime over delta t prime plus v divided by 1 plus v over c squared delta x prime divided by delta t prime. Well, this is nothing but Vx prime plus v divided by 1 plus v over c squared times Vx prime. Again, I repeat, this v is also in the direction of x. And this is how the speeds in the direction of the relative speeds of the reference frames adds up. Well, what about the y component of the speeds? Will they change or not? You see, there is one reference frame. There is the other reference frame, which is moving relative to me. And he measures the vertical component of some object. I also measure the vertical component of the speed of the same object. Will we agree or not? There is no length contraction in the vertical component. So the speed should be the same.
Time difference?
There is a time difference, though. So let's see, Vy, which is delta y divided by delta t. Delta y is the same. There is no vertical length contraction, but there is a time dilation. Delta t is just gamma delta t prime plus v over c squared delta x prime. So again, we divide the numerator by denominator by 1 over delta t prime. So we get Vy prime divided by gamma 1 plus v squared, v over c squared Vx prime. Where? This is delta t prime.
Other side of the plus sign. Yeah.
This one. 1. Okay. Don't worry, soon you will learn to decipher my handwriting. So you see, the y component also changes. And I remind you again, this is the x component of the object, the speed of the object. The change in the y component depends on the change in the x component of the x component of the speed of the velocity of the object. And similarly, Vz will be delta z over delta t. If you just do the same derivation, it will be Vz prime divided by gamma 1 plus v over c squared times Vx prime. Now let's do a very simple example. Assume that v, the relative speed of the reference frames, is equal to 0.999 c. And the observer in the other reference frame measures the speed of an object to be 0.999 c. almost the speed of light. And the y component, z component are 0. Now this is Vx primes. These are measured by the other observer. So what will I measure its speed? Vx will be, well, the addition law is Vx prime plus V. This is Vx prime is 0.9999 C plus 0.999 C divided by 1 plus V is 0.999 C divided by C squared times 0.999 C. Put in the numbers and you will find that this is less than C. Even if you put C here, even if you take this one to be C, this one to be C, this is C, this is C, so you have 2C, 1 plus C over C squared multiplied by C, it's just C. Even if there is an observer moving at the speed of light, he observes something else moving at the speed of light even further away, I will still measure the speed of that moving object to be at C. It will not be faster than C. Any last questions? If you like, we can continue also outside. Now, I am the observer. I am looking at the other reference frame, and that reference frame is moving with the speed 0.999 C. And that observer sees the object moving with a speed 0.999 C even in that direction. İyi günler.